Section: Introduction. In this section, we discuss how learning and using models of the world is a common and successful strategy in reinforcement learning, RL, especially in recent years. These world models are typically developed by training a network to predict the outcomes of actions, either directly based on the input or in a more abstract, latent space. With this broad understanding of world modeling, we're curious to see if these techniques can also benefit the learning of visual representations. Many self-supervised learning methods use structures where an encoder and a predictor work together to forecast how data will change. For example, predicting how an image might look after certain parts are masked or how it aligns with a transformed version of itself. If we think of these data changes as actions, we can draw a parallel between self-supervised learning and world modeling in RL. For instance, in masked autoencoders, the decoder acts like a world model that predicts the outcome of masking parts of an image, with the specific areas to be masked provided as additional information. Similarly, methods that focus on predicting how an image's representation changes with masking, like IJEPA or Data2Vec, are essentially learning a latent world model. If the prediction doesn't take into account how the data was transformed, the goal shifts to learning representations that don't change with those transformations, as seen in approaches like BIAL and SimSIAM, which deal with various image alterations. Despite these similarities, the world models in RL are often used in further tasks, such as planning, while in self-supervised learning, they're usually discarded after the initial training phase. This is because the main goal in self-supervised learning is to improve the encoder's ability to represent data, and most tasks in computer vision don't directly relate to the world modeling process. We believe that throwing away the world model is a missed opportunity. Just like in RL, we could reuse these models for other tasks, which leads us to explore world models as a framework for learning representations more deeply. We introduce the concept of image world models, IWM, as a strategy to not only learn effective representations but also create world models that can be reused. IWM builds on existing methods and adds the ability to handle photometric transformations, showing the importance of how the predictor is conditioned, the impact of transformation strength, and the overall capacity of the world model. We find that these world models can significantly enhance performance when fine-tuned for specific tasks, outperforming traditional fine-tuning of the encoder alone, and doing so more efficiently. Moreover, we discover that only the world models trained with IWM show this improvement, suggesting that the world model should play a central role in the learning process, rather than being discarded. Inspired by the concept of instruction tuning, we also demonstrate that these world models can be fine-tuned to handle multiple tasks simultaneously, further boosting efficiency. Our investigation highlights another crucial aspect of using world models for representation learning. The capacity of the world model directly affects the abstraction level of the learned representations. If the predictor is simple, the network focuses on high-level semantic information, capturing what's common between the original input and its transformed version. This principle underlies the success of contrastive learning, which aims to preserve the semantics of an image through transformations. On the other hand, a more capable predictor can reverse the effects of transformations, allowing the encoder to retain more detailed information about its input. This balance between a model's ability to be invariant or equivariant to transformations offers a trade-off between adaptability and performance, making world models a flexible and appealing framework for learning representations. Our contributions are as follows. We demonstrate how to use image world models, IWM, to learn both effective representations and reusable world models, highlighting the importance of transformation complexity, conditioning, and predictor capacity. We show that world models capable of equivariant transformations can improve performance in discriminative tasks. Fine-tuning the world model, rather than just the encoder, leads to better results at a lower cost. Inspired by instruction tuning, we also show that these models can be fine-tuned for multiple tasks at once. Lastly, we reveal that the capacity of the world model influences the properties of the learned representations, with invariant models leading to more abstract representations and equivariant models preserving more input details, which can enhance performance with further fine-tuning. Section Summary. In this section, we explore the potential benefits of learning and utilizing world models in visual representation learning. By introducing Image World Models, IWM, based on Joint Embedding Predictive Architectures, JEPAs, we demonstrate that leveraging world models can lead to improved performance in downstream tasks through fine-tuning. We highlight the importance of the complexity of transformations, conditioning on transformations, and the capacity of the predictor in learning representations with different properties, showing that an equivariant world model can enhance performance in discriminative tasks. Section: Related Works. In this section, we delve into the realm of augmentation invariant self-supervised learning and the concept of world modeling in visual representation learning, before introducing our method, Image World Models, IWM. Starting with augmentation invariant self-supervised learning, the essence of contrastive methods is the principle of augmentation invariance. This means that when we create multiple altered versions of an image, all these versions should be represented similarly in a hidden layer of the network, known as latent space. The challenge with these methods is to prevent these representations from becoming too similar or collapsing. To tackle this, sample contrastive methods work by distancing the representations of different images, while dimension contrastive methods prevent collapse by treating the representations collectively and striving to maximize the amount of information they contain. Interestingly, both these approaches tend to produce very similar outcomes in terms of representations. Another approach, prediction-based methods, focuses on predicting the altered representations. However, they also end up with invariant representations due to not taking into account the specific alterations made. Moving on to world modeling in visual representation learning, this concept has been successful in areas like reinforcement learning and video prediction but hasn't yet proven its worth in learning representations. Nonetheless, several methods can be seen through the lens of world modeling. Equivariant self-supervised learning methods aim to predict how data changes when it undergoes certain transformations. Masked image modeling, MIM, learns by predicting the parts of an image that are hidden. While these methods predict changes in the pixel space, their underlying mechanisms can be viewed as world models. Similarly, Joint Embedding Predictive Architectures, JEPAs, predict hidden parts of an image but do so in latent space. Recently, generative methods have been applied to representation learning. Although promising, their performance still lags behind contrastive or MIM methods, and there's evidence suggesting a trade-off between the quality of generation and the quality of representation. A common theme among these methods is that the world model, whether a predictor or decoder, is either discarded after training or only used to enhance data. We propose a new approach where we learn a world model that not only aids in learning high-quality representations but is also useful for tasks that follow. Now, let's talk about our method, Image World Models, IWM. It is based on a framework similar to Joint Embedding Predictive Architecture, IJEPA, where the predictor embodies the world model. We define a capable world model as one that can apply transformations in latent space, thereby learning equivariant representations, whereas a poor world model is considered invariant. One of the benefits of using a JEPA-like approach is that it avoids the need for an invariance loss, which is often required in contrastive methods to improve representation quality. Instead, the semantic aspects of the representation are learned through latent inpainting, allowing the network to discard irrelevant or overly complex information. This makes the JEPA approach particularly appealing since the quality of reconstruction does not directly correlate with the quality of representation. To train IWM, we first generate source and target views from an image. The target view is created by applying a random horizontal flip, a crop, and color adjustments to the original image, avoiding any destructive augmentations to preserve information. The source view is derived from the target but undergoes additional alterations, including color adjustments and destructive augmentations like grayscale, blur, and solarization, similar to those used in contrastive self-supervised learning, SSL. We also mask parts of the image following the IJEPA approach. The transformation parameters, which include information about the differences in color adjustments and whether any destructive augmentations were applied, are crucial for our world modeling. The source and target views are then processed through an encoder and its exponential moving average, EMMA, counterpart, producing representations. The use of the EMMA network is key to avoiding collapsed solutions. The predictor, acting as our world model, is conditioned with geometric information about the target and the transformation parameters. Its goal is to accurately predict the target representation from the source representation, thereby learning a useful and reusable world model. Section Summary. In this section, we explore various methods in self-supervised learning, focusing on augmentation invariance and world modeling in visual representation learning. Augmentation invariant methods like sample contrastive and dimension contrastive approaches prevent representations from collapsing by pushing away representations from other data points. World modeling approaches, such as equivariant self-supervised learning and masked image modeling, aim to predict transformations or masked parts of images to learn high-quality representations that can be reused for downstream tasks. Section: Architecture and Nomenclature. In this section, we discuss the structure and naming conventions of our model, as well as how we evaluate and improve its performance. Our model's encoder is based on a vision transformer, specifically the VIP-16 architecture. The predictor part of our model uses a similar architecture but varies in depth and the size of its embeddings. We refer to different versions of our image world model, IWM, using a notation like IWM26 number 26, where the numbers indicate the depth of the predictor and the size of its embeddings, followed by either INV or equi, to show if the model can handle inverse or equivariant transformations. For instance, IWM30 number 30 equi would mean the predictor has 18 layers, uses 384-dimensional embeddings, and can handle equivariant transformations, meaning it has learned a versatile world model. To assess how well our model has learned to understand the world, we use a metric called mean reciprocal rank, MRR. We do this by creating a set of modified images, feeding the original image through the predictor, and then seeing how close the model's prediction is to the modified image. A high MRR score means the model is good at applying the correct transformation, while a low score means it struggles. Building a strong image world model, IWM, requires focusing on three main areas: how the predictor is conditioned on transformations, managing the complexity of these transformations, and ensuring the predictor has enough capacity. We explore two ways to condition the predictor on transformations: sequence conditioning, where transformation information is added directly to the input, and feature conditioning, where this information is mixed in with the input in a more integrated way. Our experiments show that both methods can lead to effective world models, but feature conditioning tends to perform better in practical applications. Regarding the complexity of transformations, we use data augmentation techniques like color jitter, grayscale, blur, and solarization. We find that more complex transformations help the model learn better, as they provide a more challenging task for the predictor. The capacity of the predictor is also crucial. A more complex transformation requires a predictor with more depth to successfully apply it. Our findings show that deeper predictors are more effective at learning strong world models across a range of augmentations. We also visualize the predictions made by our model to better understand how it applies transformations. These visualizations show that our model can accurately apply transformations in most cases, though there are some inaccuracies, such as with inverting grayscale transformations. Finally, we discuss how world models like ours can be used in practical applications beyond just applying transformations. While our model can perform tasks like color jitter or colorization, these aren't directly applicable to many real-world computer vision tasks. We explore how our world model can be adapted for discriminative tasks like image classification and segmentation, which are more relevant to practical applications. Section Summary. In this section, we utilize the VIP-16 architecture for our encoder and predictor in the image world model, IWM. We denote instances of IWM as IWM26 number 26, where the numbers represent the depth and embedding dimension of the predictor, and whether it exhibits invariant or equivariant behavior. By evaluating the quality of the world model using mean reciprocal rank, MRR, we emphasize the importance of conditioning the predictor on transformations, controlling transformation complexity, and ensuring sufficient predictor capacity for learning a strong image world model. Section: Predictor Fine-Tuning. In this section, we delve into the process of fine-tuning the predictor for various tasks. We've discovered that for any task to be effectively tackled, the evaluation head must be adept at interpreting the learned latent space and utilizing it to address the problem. Our findings indicate that our predictor has indeed grasped valuable insights not inherently present in the encoder. However, the predictor's primary training objective, which is to forecast another valid representation, doesn't directly translate to enhanced performance in downstream tasks. This necessitates the fine-tuning of the predictor for discriminative tasks, prompting us to compare different fine-tuning protocols. Our experiments, conducted on ImageNet with VIT-B16 as the encoder, reveal several key insights. When fine-tuning the predictor, it's crucial to engage it in a prediction task. Our analysis across various prediction task definitions shows that leveraging a teacher network boosts performance beyond what a student network can achieve. Interestingly, whether or not a random transformation is applied seems less critical. The most effective strategy turns out to be predicting another full image, which offers flexibility in evaluation without being tied to the pre-training objective. Although using a CLS token for information aggregation is a cheaper alternative, it slightly reduces performance. The general results from our experiments highlight that fine-tuning the predictor maintains or even improves performance compared to other methods. Notably, an invariant behavior during encoder fine-tuning proves advantageous. Fine-tuning the predictor of an equivariant model matches the performance of fine-tuning an invariant model's encoder, showcasing the competitiveness of this approach. This method trades off parameters at inference for computational efficiency, offering higher throughput for multiple tasks compared to traditional fine-tuning methods. In the realm of image segmentation, similar trends emerge. The invariant model's encoder leads in performance, but fine-tuning the predictor with an equivariant model significantly outperforms encoder fine-tuning. This underscores the versatility of our approach for a broad spectrum of tasks. Efficiency comparisons further validate the merits of predictor fine-tuning. When parameters are comparable, predictor fine-tuning with our method outshines encoder fine-tuning, underscoring not just competitive performance but also efficiency and adaptation. A comparison involving the end-to-end fine-tuning of a VIT-B with the encoder fine-tuning of a VIT-L reveals performance gains with fewer parameters, highlighting the effectiveness of leveraging the world model learned through our approach. In summary, our exploration into predictor fine-tuning demonstrates its potential to enhance performance across various tasks and its efficiency in adaptation, making it a compelling alternative to traditional fine-tuning methods. Section Summary. In this section, we explore predictor fine-tuning and its impact on various tasks. We find that fine-tuning the predictor with an equivariant model can significantly improve performance over encoder fine-tuning, showcasing the potential of leveraging the learned information in the predictor for different tasks. Additionally, we observe that predictor fine-tuning with an invariant world model, IWM, not only enhances performance but also proves to be more efficient compared to encoder fine-tuning, demonstrating the effectiveness of this approach in adapting to new tasks. Section: Multitask Predictor Tuning. In this section, we delve into the concept of multitask predictor tuning, building on our earlier discussion about the efficiency gains over traditional encoder fine-tuning. Our primary aim in representation learning is to craft representations that are versatile enough for a broad array of tasks. By training the predictor on various tasks, such as colorization, inpainting, and color changes, we've discovered that it can also be fine-tuned for multiple tasks simultaneously. This approach draws inspiration from prefix tuning and instruction tuning in large language models, LLMs. Essentially, we introduce new, learned tokens that signal to the predictor the specific task it is addressing, a strategy reminiscent of Ditox's use of task tokens for continual learning. For each task, we assign a unique task token, alongside a task-specific head and/or loss function. We then aggregate all task losses, updating both the predictor and the task-specific heads accordingly. We explore a straightforward scenario where tasks are evenly distributed within a batch, though we acknowledge that alternative sampling strategies might enhance performance further. Our evaluation, conducted on a model pre-trained on ImageNet and tested on ImageNet, iNaturalist 18, SUN 397, and Places 205, involves comparing a single task baseline, where the total number of iterations matches that of the multitask training, to the multitask approach. This comparison reveals that training 4 separate single-task baselines incurs the same cost as multitask training but results in 4 distinct models instead of one unified model. Remarkably, the multitask predictor achieves comparable, if not superior, performance to the single-task predictors, with a notable improvement on SUN 397. On average, its performance aligns with that of the single-task models, underscoring the efficiency benefits of leveraging robust world models that share parameters across tasks, thereby streamlining predictor fine-tuning and inference. When a comprehensive world model is successfully learned, it can be repurposed for downstream tasks through fine-tuning, offering competitive performance with encoder fine-tuning but at a significantly reduced cost. This efficiency can be further enhanced by adopting a multitask fine-tuning strategy, showcasing the method's adaptability. To round off our analysis of image world models, IWM, in representation learning, we examine their performance in lightweight evaluation protocols commonly used in self-supervised learning, focusing on linear and attentive probing. Our findings indicate that when IWM learns an invariant world model, it mirrors the behavior of contrastive methods like MoCoV3, achieving substantial gains in linear evaluation over masked image modeling, MIM, or other joint embedding predictive approaches, JEPA. Conversely, when IWM learns an equivariant world model, it behaves similarly to MIM methods such as ME, showing lower performance in linear evaluation but more competitive results in attentive probing. This suggests that the key difference between methods may not lie in the quality of the representation per se, but rather in the level of abstraction and how readily information can be extracted from them. We observe a clear correlation between the most suitable evaluation protocols and the equivariance of the world model. More invariant models excel in linear evaluation, while equivariant models perform better with larger evaluation heads, as seen in predictor fine-tuning. Moreover, the richer representations produced by equivariant world models lead to improved performance on out-of-distribution datasets. This allows us to position different approaches along a spectrum of representation abstraction, with contrastive methods at one end, offering high abstraction but lower peak performance when adaptation costs are disregarded, and masked image modeling at the other, providing stronger performance in complex evaluations but struggling in linear probing due to less accessible information. By adjusting the equivariance of the world model, IWM spans this spectrum, bridging the gap between contrastive approaches and MIM. This spectrum encapsulates the self-supervised learning ethos of learning what is predictable, highlighting that a weak world model may fail to adequately model the world, leading the encoder to discard unpredictable information. Conversely, a powerful world model enables the representation to be less abstract or semantic, as it can predict representations in any scenario, offering a tangible means to modulate the abstraction level of the representations.